Now, let us do this result. We proved similar result in the case of discrete random variables. So, we have a similar result for absolutely continuous random variable. So, let x equal to x1, x2, xp be a p dimensional absolutely continuous random variable. Suppose their joint PDF is fx and marginal PDFs are suppose fxi. So, that means xi has a marginal PDF fxi. Then x1, x2, xp are independent if and only if their joint PDF can be written as product of marginals. So, we proved a similar result in case of discrete where these PDFs were PMFs. Now, the same arguments can be used to prove the result for absolutely continuous random vector. So, x1, x2, xp would be independent if and only if joint PDF or joint PMF is same as product of marginals. Now, one of the conclusions is if x1, x2, xp are independent, then the support of the random vector x is same as cross product of support of individual random variables. So, independence shows this. So, that means if this is not happening, then you can conclude that x1, x2, xp are not independent. Let us do another result, which is again simple to prove. So, let x1, x2, xp be absolutely continuous random vectors of different dimensions. Before I go for this, let me actually this result holds for random vectors also. I can say that random vectors x1, x2, xp are independent if joint distribution joint PDF of x1, x2, xp is same as marginal of product of marginal of x1, x2, xp. And similarly, this result also has analog for random vectors. So, that means random vector x1, x2, xp would be independent. If they are independent, then the joint support of x1, x2, xp would be same as support of x1 cross support of x2 cross support of xp. So, now let us do this result which says if let x1, x2, xp be random vectors which are absolutely continuous and suppose they are possibly of different dimensions, then x1, x2, xp are independent if and only if for any arbitrary functions psi 1, psi 2, psi p, psi 1 x1, psi 2 x2, psi p xp are independent. So, random vectors are independent if and only if you take any arbitrary functions of those random vectors, they are independent. The second part of this result says if x1, x2, xp are independent if and only if probability that xi belongs to ai for I is equal to 1 to p is same as product of probability xi belonging to ai for any sets a1, a2, ap. This of course, we have seen in the case of distribution functions joint this in case of if these sets were of the type minus infinity to x, then this is equivalent to saying that joint distribution function is same as the product of marginal distribution functions. Now, just remark over here result 3 remains valid with obvious modifications for independence of absolutely continuous random vectors. That is what I repeated a few moments back. Another thing is random vectors x and y are independent if f of y given x, y given x is same as f y y. Because what we have seen is f y given x, y given x, one can see is same as f y x, y x divided by f x x. And if they are independent, this joint would be same as product of f y x, f x x divided by f x x, and this gets cancelled. So, this would be same as f y y. And it happens if and only if these all conditions are if and only if. Similarly, x and y are independent if and only if, because we have seen that they are independent if and only if the joint PDF is same as f x x into f y y, which is equivalent to saying that f x y x y divided by f x x is same as f y y. Now, this is nothing but joint divided by marginal, which is a conditional PDF of y given x is same as the unconditional PDF of. So, this says which intuitively also makes sense that if x and y are independent, then an information that x is same as x should not alter the probability. probability density function or the distribution function, and that is what is being concluded over here. X and y would be independent if conditional PDF is same as the unconditional PDF, or the conditional distribution function is same as the unconditional distribution function. Let us do this result, which again we proved for the discrete case. For the absolutely continuous case, the proof is exactly on the similar lines. So, let x equal to x1, x2, xp be an absolutely continuous random variable with joint PDF of x. Then x1, x2, xp are independent if and only if the joint PDF of x1, x2, xp can be factored in such a way that I can separate out the terms of x1, x2, xp. That is what it is said over here. If joint PDF is same as C times product I is equal to 1 to P gi xi for x equal to x1, x2, xp belonging to R. For some non-negative functions gi's defined on R and some positive constant C. In fact, in this case the marginal PDF of xi will turn out to be, you will have to integrate out the unwanted variables. So, you will get only gi x and then some constant would come. So, marginal PDF of xi would be nothing but ci times gi x. So, this sometimes turns out to be very handy in verifying whether given random variables or given random vectors are independent or not. If we are in a position to separate out the terms of x1, x2, xp in the joint PDF, and if your support can be written as cross product of support of x1, x2, xp, then I can conclude that the random variables x1, x2, xp are independent. Of course, this result has an obvious modification to case of random vectors. So, result 5 remains valid with obvious modifications for independence of absolutely continuous random vectors of possibly different dimensions. So, let us consider this example quickly. Let x1, x2, x3 be absolutely continuous random variable with joint PDF given by this. So, range is 0, x3 less than x2 less than x1, where C is a fixed real constant. Determine C and support of x, find the marginal PDF of x2, x3, find the marginal PDF of x1, x2 and x3. For fixed 0 less than x3 less than x2, x less than x1, find the conditional PDF of x1 given x2, x3 is equal to x2, x3. Then for fixed x2 belonging to 0, 1, find the conditional PDF of x1, x3 given x2 is equal to x2. Are x1, x2, x3 independent? Now, this independence, as I said before, can be checked very quickly over here. First of all, here if you look at the structural form, this I can separate out the terms of x1 and x2, but if I look at the support Sx, Sx is collection of all those x belonging to R3 such that 0 less than or equal to x3, these boundaries will have to be included in the support, because the moment I take a neighborhood I enter into this region, and since I will be integrating a positive quantity in that probability would be positive. So, these are support, but if I look at the support of only x1, support of x1 is nothing but 0 to 1, because x1 will take value 0 to 1. Support of x2 is 0 to 1, support of x3 is 0 to 1. So, clearly this Sx is not same as the cross product of 0 1 0 1 cross 0 1. In fact, this is much bigger set, because Sx only takes a restricted part of it. So, I can just by looking at the joint PDF, I can conclude that the random vector variables x1, x2, x3 are not independent. Let us try to see this one by one. So, to get the constant C, I know that it is a PDF, so it should integrate out to 1. So, my PDF is C upon x1, x2 over the range 0 less than x3 less than x2 less than x1 less than 1. So, this is the range. So, I have to integrate this over this range. So, first what I do is first I make x1 as a free variable. X1 as a free variable can go from 0 to 1. So, this is the range of x1. Now, x1 has been fixed. Now, I try to integrate x2. For a fixed x1, x2 can go from 0 to x1. For a fixed x1, x2 can go from 0 to x1. So, this becomes x2. Now, x1 and x2 are fixed. So, for fixed x1 and x2, x3 can go from 0 to x2. So, this is the range for x3, C of x1, x2. So, you just integrate it out, it is a simple integral. This turns out to be this, and this gives me the value of C to be 1. So, you have to be just a little bit careful in the range of integration, rest of the things are simple and also clearly for c is equal to 1, the function f x x is always greater than or equal to 0. And as I said before, the support in this case is collection of all those x 1, x 2, x 3, x belonging to R 3 such that probability x belonging to an R x is positive. So, these boundaries will anyway come into the picture, because whenever you take any neighborhood on the boundary, it will go to the interior, and then you will be integrating the positive function in the interior. So, it will be positive. So, normally support these boundary points will always be included, whatever may be the situation. Now, let us look at the joint PDF of x 2 and x 3. So, to get the joint PDF of x 2 and x 3, I have to integrate out the unwanted variable for fixed x 2 and x 3, because I am talking about PDF of x 2 and x 3 at fixed point x 2 and x 3. Note that my range of integration is 0 x 3 less than x 2 less than x 1 less than 1. So, my x 2 and x 3 are fixed. I have to integrate out the unwanted variable, which is x 1. For fixed x 2 and x 3, x 1 can go from x 2 to 1. So, that is what is happening. X 1 is going from x 2 to 1, and function was 1 upon x 1 x 2 t x 1. So, if you integrate out, this turns out to be this. So, this is the joint PDF when range is this, because if this function is positive only in the range 0 less than x 3 less than x 2 less than x 1. So, let us give a summary. So, joint PDF of x 2 and x 3 turns out to be this quantity if 0 less than x 3 less than x 2 less than 1 and 0 otherwise. So, I found out the joint PDF of x 2 and x 3. If I want, I can get the marginal PDF of x 2 and x 3 from here only by integrating out the unwanted variables. So, let us look at the marginal PDF of x 1. So, to get the marginal PDF of x 1, the unwanted variables are x 2 and x 3. So, I integrate out x 2 and x 3 in the joint PDF. Now, my x 1 is fixed. I know that my PDF is positive in this range. My x 1 is fixed, because I am talking about PDF of x 1 at the point x 1. So, first for this x 1, I take x 2 as a fixed variable. X 2 as a fixed variable can go from this x 1 is fixed. So, x 2 as a fixed variable can go from 0 to 1. So, that is what x 2 is. So, now my x 2 is fixed. Now, for fixed x 2, x 3 can go from 0 to x 2. So, this x 3 can go from 0, and my PDF is 1 upon x 1 x 2 dx 3 dx 2. So, if you integrate, this turns out to be this in the first step, and this total turns out to be. So, f x 1 turns out to be this quantity if 0 less than x 1 less than 1. In other range, I know that this PDF would be 0. So, it will be integrating out 0. So, you get 0. Now, I can get the marginal PDF of x 2 from the joint PDF of x 2 and x 3. Note that x 2 and x 3 have this support. So, here if I integrate out x 3 for a fixed x 2 can go from 0 to x 2, and if I integrate out x 2 for a fixed x 3, x 2 will go from x 3 to x 1. So, I can get the marginal PMFs of x 2 and x 3 from joint PMF of x 2 and x 3 in the following manner. So, f x 2 x 2. So, I integrate out x 3, and we have seen that because 0 less than x 3 less than x 2 less than 1. So, I have to integrate out x 3 for a fixed x 2. For a fixed x 2, x 3 can go from 0 to x 2. This was the joint PDF of x 2 and x 3. So, this turns out to be minus log x 2. So, f x 2 x 2 turns out to be this quantity. If 0 less than x 2 less than 1, it is minus log x 2, and this is 0 otherwise. Similarly, for 0 less than x 3 less than 1, f x 3 x 3 would be integrating out the unwanted variable x 2 over here. Now, for fixed x 3, x 2 can go from x 3 to 1. So, this is what is happening over here, and this is a joint PDF of x 2 and x 3. And if you integrate out, this turns out to be log x 3 whole square by 2. So, this turns out to be this. Now, let us try to see for a fixed 0 less than x 3 less than x 2 less than x 1, what is the conditional PDF of x 1 given x 2 and x 3. We know that conditional PDF is same as joint. So, f of x1 joint PDF of f of x1 x2 x3 at the point x1 x2 x3 divided by marginal of conditional variable conditioned is x2 x3. So, marginal PDF of x2 x3 at the point x2 and x3. So, you put those values and you get this. Now, let us look at what is the conditional PDF of x1 x3 given x2. So, this turns out to be joint PDF of x1 x2 x3 at point this divided by marginal of condition which is f x2 x2. Now, here x2 is fixed. So, this turns out to be minus 1 upon x1 x2 log x2 if x2 less than x1 less than 1, 0 less than x3 less than x2. So, I have broken it into two parts because my x2 was fixed. So, note that here if x2 is given, the support of x1 x3 can be broken into two parts, and here also x1 and x2 can be separated out. So, this suggests that if x2 is given, x1 and x3 seem to be independent, and that is what we will conclude later on. So, one thing we have clearly seen that fx1 x2 x3 is not same as fx1 fx2 fx3, which implies that x1 x2 x3 are not independent. This also follows from the fact that Sx is not equal to Sx1 cross Sx2 cross Sx3, that we saw in the beginning itself, that x1 x2 x3 are not independent because this does not happen. So, one can argue non independence of x1 x2 x3 follows from this fact as well. For fixed x2 belonging to x1, f of x1 x3 x2 x1 x3 x2 can always be written as g1 x1 g2 x3 for x1 x2 x3 for x1 x3 belonging to R2, where g1 x1 is this quantity, g2 x3 is this quantity. As I told you that given x2 is equal to x2, I can separate out the terms of x1 and x3 over here, and that is what I am doing over here. So, this turns out to be this, and this turns out to be this. That is what we saw in the last slide, that you can separate out the ranges x1 because x2 is fixed. So, x1 between x2 to x1 and x3 is between 0 to x2 because x2 is fixed, and here also I can separate out x1 and x3 because x2 is a constant. So, there is no x3 term. So, x1 and x3 in a sense are being separated out. So, this is what is happening. So, thus given x2 is equal to x2, x1 and x3 are independent. So, now let me give a take home problem. So, let x equal to x1 x2 be absolutely continuous and dumb variable with PDF given by this. Now, here again because I cannot separate out x1 and x2 in the range, this suggests that x1 and x2 will not be independent, just by observation you can say. Now, here c is a fixed constant, find the value of c, find the marginal PDF of x1 and x2. For fixed x2 belonging to 0 1, find the conditional PDF of x1 given x2 is equal to x2. For fixed x1 belonging to 0 1, find the conditional PDF of x2 given that x1 is equal to x1. Are x1 and x2 independent, which of course one can say just through observations that they will not be independent, because Sx will not turn out to be same as Sx1 cross Sx2. Now, before I conclude, let me give a summary of the next module. In the next module, we will study the expectations and movements of random vectors. So, this was all for this module. Thanks for your patience and have a great day.